about what can we learn from the current Higgs data. I'm going to use the TT bar axis as an example. And then I realized it may be a bad idea to give this talk because I don't even know if that axis is still there, and some of you guys must have a much better idea than I do. So stop me if you know this axis is already gone, or
you can turn.
Okay. So. Okay, so I'll continue. So let me start with the current Higgs profile. So, so here is a combined analysis by Atlas and CMS. The data goes in this plot is the full data set from 7 and 8 TeV. This is a 7-parameter fit in the kappa framework. The kappas here are the measured effective Higgs coupling normalized to the standard model value. And a 7-parameter fit means there's no one-to-one correspondence between kappa T here, between kappa T and the kappa blue and kappa gamma. That means new particles are allowed in the effective vortex. So after we discovered the Higgs, we measured the Higgs mass, we measured the Higgs couplings, and we often hear the statement that the Higgs is very likely to be the standard model Higgs. But if we take a close look at the Higgs profile, it's not exactly true. So I think there are two very interesting deviations from the standard model, and both are in the Higgs coupling to the third generations. The first one is this one, so kappa B. So this is a deficit here, and it corresponds to more than 2 sigma. Kappa B is important because it controls the Higgs width. So a smaller kappa B means the Higgs width is smaller than the standard model value, and that means the branching ratio to all other channels are larger than what we have in the standard model. So I think this one is very interesting and does not draw much attention, but I'm going to talk about the other one, the Higgs coupling to the top part. So this one is higher than the standard model, so the best fit value is about 40% higher than the standard model value. And it is almost a 2 sigma axis. This axis is normally driven by the axis in TT bar Higgs to WW multi-electron channel. The reason I think this axis is interesting is because we have seen this axis in both experiments. So here is the result from run 1, both CMS and Atlas. This one is from CMS. The largest axis is from same sign dilepton channel. The signal stress is a little bit higher than 5. And that corresponds to a local significance of 2.6 sigma. Atlas sees something very similar. So in the multi-electron channel, Atlas sees a signal strength of 2.1. Not only we have seen this axis in both experiments, we have seen it in both runs. So here is the signal strength from early branch 2 data, and the CMS see a signal strength of 2.0, Atlas see a signal strength of about 2.5. So of course this is not 750, but we have seen it in both experiments, and we have seen it in both runs. So I think that is something worth paying attention to. So in this talk, I'm going to talk about 2 possible interpretations of this axis and the implications for future variants. So when you see an enhanced TT bar Higgs, what's the most naive thing you can do? The most naive thing you can do is you say, we just have the standard model, but we have an enhanced Tau-P-Kava. There are 2 problems with these explanations. The first one is, if we have an enhanced Tau-P-Kava here, this coupling also contributes to the gluon fusion process. So if the TT bar axis is from an enhanced Tau-P-Kava, that means we should see an axis in the gluon fusion as well. But gluon fusion probably is the best measured channel at the LHC. Is quite standard model-like. So there are some discrepancy here. If we have standard model and enhanced TAMU cover, we should expect the gluon fusion to be high as well. So beyond the fact we don't see an access in gluon fusion, large TAMU cover just in the standard model can be quite dangerous. The reason is the TAMU cover contributes to the running of the quartic coupling to the fourth power. That means even a small perturbation in the TAMU cover can completely change the running of the quartic coupling. So here I plot the running of the Higgs self-coupling. The red curve here is the standard model case, and in the blue curve, I put a 3% perturbation in the TAMU cover. So this is just a naive example, and you can see the Higgs self-coupling becomes negative at around 100 TeV. So we have an unstable vacuum. And a more detailed calculation shows a 0.45% deviation in the TAMU cover. The lifetime of our universe is smaller than the lifetime of our vacuum is smaller than the age of the universe. So that is something we don't like. So we don't see an access in gluon fusion, and also we don't like a TAMU cover just in the standard model. So the explanation I want to use here is, what if the TAMU cover is a standard model like, but the access is actually from something else, has nothing to do with TT bar Higgs, but it just happens to have the same signature, so we call it TT bar Higgs. So if we look at other channels, say Higgs decay to BB bar or Higgs decay to gamma gamma, so those channels are more Higgs oriented. So if I combine the access, which the signal strength is about 5, with other channels, I have a signal strength about 2.8 CMS. So the access becomes less significant. And same thing in Atlas. In Atlas Higgs to multi-lepton, the signal strength is about 2.5. But in the TT bar Higgs combination, goes from 13 TeV and 8 TeV. So in this combination, only Higgs to gamma gamma and Higgs to BB bar is included. And you find the signal strength is is much more standard model, like the signal strength is about 1.8.
Can I ask you a question about the data? Those bottom three categories, is that, can I read that? Is that 4L, 3L, and same sign 2L?
The Atlas one?
Yeah.
So yes, 4L, 3L, and 2L.
So are those exclusive? Like an event with 3 leptons is going to have 2 that also have the same sign. Right? So are they subtracting out?
Oh, you mean if 3 leptons subtracting?
Well, if you have 3, for sure you have a same sign pair, right?
I think they don't subtract that.
So those 2 points have a large overlap between.
3 lepton and 2 lepton, yeah. Yes.
Okay. Okay.
Yeah. Okay, so since you mentioned that, probably let me mention another thing. So so this is the run 1 data, and the axis is in sim-sign dilepton, and the trilepton is standard model like. But in run 2, the axis is in trilepton, and sim-sign dilepton is standard model like. But if you just take a combination in multi-lepton, the axis is always there. All right, so what I just told you is if we only look at the multi-lepton final stage, we have a large axis. But if we only look at BB bar or gamma gamma, the signal strength is much closer to 1. So then we want to ask, when we call the axis TT bar Higgs, is that really a TT bar Higgs or something else? So let's take a closer look at the signature. So when we say we're looking at a TT bar Higgs to WW, what are we seeing exactly? So since in the analysis we never try to reconstruct the Higgs or the top, we are actually looking at a 2 top plus 2 W final state. Or since we did not even reconstruct the top, we're looking at a 2B plus 4W final state. And then the 2B and 4W give rise to multi-lepton, multi-B, and missing energy signature. So when we talk about an axis in TT bar Higgs, we don't know if it is a TT bar Higgs. We only know we have an axis in multi-beam, multi-lepton, and missing energy channel. So when I tell you there is an axis in multi-beam, multi-lepton, missing energy, you're not going to tell me this is an axis in TT bar Higgs or TAMU Kava. You're going to say this is an axis for new physics. And that is exactly what CMS did when CMS looked for spot pair protection. So when CMS looked for spotums decay to a top and trigonal, CMS looked exactly for a 2 top and 2 W final state. So of course I can interpret the TT bar Higgs axis in terms of spot pair protection, but I choose not to do that because we want to do something in the simplified model, and if we want to explain this signal in the simplified model, there is a caveat. Because in the simplified model, we always assume a 100% decay branching ratio, and this diagram will never give me a 100% branching ratio, because for spotums, this decay chain is always there, the spotum decay to a bottom and the neutralino. So let me emphasize again, of course we can explain this axis in terms of spotums. I just choose not to do that for simplicity. So what would give me a 100% decay branching ratio is a stop. So if I have a pure red-handed stop, it is not coupled to Reno. So if I decouple the Higgs zeros, the stops can only decay to a top and Reno. Can only decay to a top and a Reno. So now I have a 100% decay branching ratio here, stops decay to a top and a Reno. And then for the Reno decay, the Reno can decay to a W and a tribe Reno or a Higgs plus a neutral Reno. So here I want a W here, so I say I put the mass difference between the Reno and Reno to be smaller than the Higgs mass. So I suppress the decay to Higgs kinematically, and I have a 100% decay branching ratio to W and tribe Reno. So I have the stops pair produced, each of them decay to a top and the Reno. The Reno decay 100% to a W and charge Reno, so I have 2 top and 2 W final state. So let me show you a spectrum. So since this one has exactly the same final state as sputum decay to top trigonal, I need to look at the bounds from sputum pair production. So here is the bound for sputums in the top trigonal decay chain. Since my LSP is window-like, so the bound that is relevant is the mass of the neutralino 1 and trigonal 1 very close to each other. So I look at the bound where the mass ratio is about 0.8. And then one thing you can see from this plot is the bound almost disappear if the LSP is heavier than 240. So based on that, I put my LSP mass at 260 GeV. And then again, because I don't want to decay through the Higgs, I put the Bino mass to be smaller than the LSP plus 125. So let's call it 340. Then to choose the stop mass, I want to have a signal strength in the same sign dilepton channel about 2.8. So I choose stop mass about 550, and that will give me a signal strength about 2.8. So now I have a real spectrum. I'm about to make some very dangerous statement that may be excluded by now. So that benchmark I proposed is from the HTV axis. So what do we expect at certain TV? The first obvious thing is stops are much heavier compared to TT bar Higgs. So I would expect this stop cross-section grows much faster compared to TT bar Higgs just from the PDF. So indeed, it grows the ratio of certain TV to HTV cross-section for stops is about 6.7, and TT bar Higgs is about 4. So Then if I take my benchmark, which gives me a signal stress of about 2.8, I'm going to see a signal stress about 3.7 at 13 TeV. Also, stops and TT bar Higgs will give me very different kinematics. So first, for this, in the stop signal, the missing energy is from the neutrino, and in TT bar Higgs, the missing energy is from the neutrino. So I expect the missing energy to be much harder in the stop case. And indeed, here I plot the distribution of missing energy for stop signal, which is the blue one, and TT bar Higgs enhanced by a factor of 2.7, so they have the same cross section in the red one. And you can see the missing energy is much harder for stops. And also for TT bar Higgs, because of the T-channel kinematics, I expect the beams from the tops to be a little bit more forward. And in stops, I expect the B jets to be more centrally produced. So here is a distribution of eta B. So it's not quite significant, but the tops from stops are a little bit more central. So then if I want to see this signal quicker in certain TeV, I'd like to move the cut of missing energy to 125, and also move the cut of eta B to about 1. And if I do that, I use my old benchmark. I expect a signal stress about 7, and we should already reach 5 sigma for the current data we have. So if you're interested, you can look into the data and tell me that it's there. Also, another thing is here, LSP is window-like, so and we have pretty light windows, and we expect this disappearing tracks. So whether or not we're going to see the disappearing tracks depends on other parameters in the model. So, for example, in the benchmark I showed you, we proposed a window about 260 GeV. So if this window is a pure window, then the mass splitting between the neutral and charged window is about 160 MeV, which is about the current CMS limit. But just as I told you, that depends strongly on other model parameters. Even if we mix the window with some Higgs component, the mass splitting can increase significantly. So even I put the Higgs signal around 1 TeV, then the mass splitting between the neutral and charged window is about 240 MeV, which is pretty hard for CNS. Another thing that is quite unique for this scenario is we expect same sign trilepton in this case. So we have 2 stops pair produced. Then the stops decay to top and bino. The charge so the 2 tops from the stop decay, they have opposite charges. And then the bino can decay to a charged window, and the W, we're not going to see the charge of the charged window because the soft leptons from the window decay are just too soft. So we're only going to see the charge of the W. Then it is possible that the 2 W's from the window decay have the same sign because the window decay is charge symmetric. So once the 2 W's from the window decay have the same sign, they always have the same sign with one of the tops. So we have the possibility of seeing 3 same sign leptons. So this is something almost background free. And with the current data, we should see 5 same sign trilepton signal. So the first explanation I just discussed about the Higgs axis is the coupling is standard model-like, that the axis is from stop pair production, and we expect the signal stress to be higher at 13 TeV. And also, we may see same sign trilepton and the disappearing tracks. So again, those are probably some very dangerous statements because we already have for the inverse rental barn, and So the benchmark I proposed may be well excluded already. So I'm going to, so in the next 20 minutes or so, I want to discuss something that's not going to be excluded so soon. So I just told you we cannot have enhanced Chapter in the standard model. So what about we have enhanced Chapter and new physics? So here I write down all the dimension 6 operators that are relevant for TT-bar Higgs and gluon fusion. The first term is the Higgs coupling to two tops, and that controls both TT-bar Higgs and gluon fusion. So if I have an enhanced Chapter, I should expect the TT-bar Higgs to be high, gluon fusion to be high as well. But since we see a standard model like gluon fusion, we want something else to cancel the contribution from an enhanced Chapter. So if the second term, which is the effective Higgs gluon coupling, can cancel the contribution from an enhanced Chapter in the gluon fusion, we can still have this gluon fusion standard model like. So you can see there are some degeneracy in gluon fusion. We cannot really tell if an axis is from TT-bar Higgs or from effective Higgs coupling to gluons. So again, let's go back to the axis. The axis indicates an enhanced coupling, and that indicates a modified effective gluon Higgs coupling. A modified Higgs to gluon coupling implies we have a modified triangle diagram, and that means we have new particles running in this loop. Both modified Higgs top-top coupling and new particles in the loop have an effect on double Higgs production. So in the standard model, there are two diagrams contributing to double Higgs: the triangle diagram and the box diagram. Both are sensitive to a modified top coupling. The triangle diagram is sensitive to the top coupling square, and the box diagram is sensitive to the top coupling to the fourth power. Both of them are sensitive to the new loop particles, and good thing is they have different form vectors. In addition, the triangle diagram is also sensitive to a modified trilinear coupling. And the trilinear coupling can be modified for good reasons from the theory side, because the trilinear coupling is closely related to the nature of electroweak phase transition. So let me remind you about the three conditions for electroweak baryogenesis. So we need some process that generate extra baryons. So we need a baryon number violation. And the second one is CP violation. So otherwise, for each process that can produce matter over antimatter, the CP mirrored inverse process will produce antimatter over matter. And the third condition is we want the departure from thermal equilibrium. So we need a first order phase transition. Otherwise, for each process produce matter over antimatter, the inverse process can produce antimatter over matter. So electroweak phase transition is something very important for cosmology, but that is something hard to study from cosmology. So we want to see if we can study the nature of electroweak phase transition from the particle physics side. And electroweak phase transition in the standard model is not first order unless the Higgs mass is very small, say about 40 GeV. And that means we need new physics for a strong first order phase transition. This new physics will alter the finite temperature Higgs potential, so has a boundary at the critical temperature. And the good thing is the Lagrangian that described the finite temperature physics is exactly the same as the zero temperature physics other than a temperature effect. So we can measure the zero temperature Higgs potential at LHC to learn about the finite temperature Higgs potential. So what do we know so far about the Higgs potential? In the standard model, the Higgs potential is completely specified by these two parameters. And we have measured a couple of things about Higgs potential. So we have measured the Higgs mass from G Fermi. And also, we have measured the second derivative of the Higgs potential because we measured the Higgs mass. So the third thing we want to measure is the third derivative of the potential, and that is the Higgs trilinear coupling. So, as I said, the Higgs potential is closely related to the nature of electroweak phase transition, and therefore, at the LHC, the way to probe it is the nature of electroweak phase transition is related to the Trilinear coupling. There are a lot of models that would give you a first-order phase transition. So here are just some examples of it. Higgs standard model plus a singlet plus a scalar doublet. You can think of MSSM stop, and standard model plus chiral fermion. You can think of MSSM neutrinos. Standard model plus Brownian Yukawa. You can think of it as a flareon. So we have calculated the trilinear coupling in those models, and one thing we find is trilinear coupling can deviate significantly from the standard model value in the region that can be consistent with a first-order phase transition. And in those calculations, we find order 1 deviation is typical, and the trilinear coupling can go to S log S7, the standard model value in some of those models. So now we have three things that can affect a double Higgs projection. So we have enhanced TAMU cover, which is indicated by the data, and also the fact that the gluon fusion is standard model-like indicates there are new particles running in the loop. And then trilinear coupling can be modified for, then it is well motivated to think of a modified trilinear coupling from the nature of electroweak phase transition. So now let's see if we put all the three things together, what is the implication for a double Higgs? So first, let's see how does a modified trilinear coupling affect the double Higgs. So there are two diagrams contributing to the double Higgs production at the LHC, the triangle diagram and the box diagram. They interfere with each other destructively. So here is the production cross-section for double Higgs for different values of the trilinear coupling. So there are two things I think worth noticing in this plot. The largest cancellation is when the trilinear coupling is about 2.5, the standard model value. So that means if there are some degeneracy in double Higgs from gluon fusion. So that means if we measure the double Higgs production cross-section at the LHC, we don't really know the trilinear coupling because of this degeneracy. So we don't know if it is standard model-like or about 4 times the standard model because they all give exactly the same number of events at the LHC. And another thing is, I just told you in models with a first order electroweak phase transition, the trilinear coupling can be as large as 7 lambda 3 SM. So that seems to be a very large enhancement, but in terms of cross section, it's not that large enhancement. Say from 1 to 5, in the trilinear coupling, the cross section is only increased by about a factor of 2. So now let's look at decays. So when we think of the decay of one Higgs, we can have the Higgs decay to a pair of Bs. This one has a very large decay branching ratio, but it also has a large background as well. And then to the other extreme, we can think of the Higgs decay to a pair of Z. Then Z decays to photon or gamma gamma. Those are very clean channels, but they also have very low branching ratio. And WW and tau tau, they have sizable branching ratios, but it is a hard measurement because there are missing energies involved. So the strategy to think of the decay of double Higgs is we always have one Higgs decay to a pair of beams for statistics. Because double Higgs is a very rare process, the cross-section for double Higgs is 3 orders of magnitude smaller than single Higgs. And then we have the other Higgs decays to a pair of photon or ZZ, WW or tau tau, so we have some handle over the background. I'm going to use BB gamma gamma just as an example here. So there is an atlas study in this channel, and this is the atlas result here. So in this note, atlas say the projection of exclusion for BSM models or the trilinear coupling smaller than negative 1.3 standard model value or larger than 8.7. So I think there is something very confusing when I just look at this plot. So as I told you before, if I think of cross-section from 1 to 5, the cross-section is increased by a factor of 2. But if I look at the significance plot, the significance for lambda equals 5 is much smaller compared to the standard model case. So atlas basically is saying they don't have any sensitivity when the trilinear coupling is 5 times the standard model case. So I think that, so let's try to understand what's going on here. So to understand that, let's look at the cats atlas has been using. So let's go through this chart. So they require 2 photons and the 2 B jets, so nothing special there. And then they require the numeric mass of the 2 Bs and the numeric mass of the 2 gammas within some range of the Higgs mass to make sure 2 Higgses are reconstructed. And then these 2, unless we took extra leptons or jets, so those are to suppress the TT bar Higgs background. And then atlas require the delta R of the 2 Bs and 2 gammas in some window. There's nothing wrong with that. But in addition, atlas require the delta R between B and gamma to be larger than 0.4. So this is something that makes total sense. But if I combine this cat with the other cat, the PT cat of the Higgs, effectively I make a cat on the inverted mass of the 2 Higgs. So not only atlas effectively put a cat on M Higgs Higgs, in most of the theory studies, M Higgs Higgs larger than 350 is always required. So since there's nothing special about all other cats, this cat is responsible for the significance goes down for large value of the trilinear coupling. And let's try to understand that. So to understand that, I plot the amplitude for different values of MHH, and the trilinear coupling is chosen to be 2.5, where the largest cancellation happened. So when MHH is below the 2 m top threshold, there are only real parts in amplitude, and you can see the destructive interference between the box and the triangle diagram. And it cancels each other completely when MHH is at the 2 m top threshold. Then when MHX crosses the 2 m top threshold, the amplitude starts to develop imaginary parts. So separately, there are still cancellations between the real parts and imaginary parts, but if we think of in terms of cross-section, the cancellation is not there anymore. That means if we increase the value of the trilinear coupling from here, I'm going to increase the amplitude more below the 2 m top threshold compared to above the 2 m top threshold. Then if I look at the distribution of MHH, I'm going to see the distribution shifts to smaller values for large values of the trilinear coupling. So here I plot the normalized Higgs distribution for different values of the trilinear coupling. The red one is the standard model case, and the black dashed line here is MHH equals 2 m top. So then you see the logic of applying a cat at 2m top. So for the standard model case, if I apply a cat at 350, then I keep most of my signal. And the background in this channel is most of them is just QCD, so it tends to be soft. So this cat is very effective for the standard model case. But then if I increase the trilinear coupling to 2.5, which is the blue one here, so this one probably is not interesting on fires because this one has very low cross section because of the cancellation. I just plotted here so you see there is an exact cancellation at the 2m top threshold. Then I continue to increase the value of trilinear coupling from the blue one. I increase more below the 2m top threshold than above the 2m top threshold. So when lambda 3 is 7, lambda 3 SM, I have a very soft distribution for FHH. So that means if I'm targeting new physics with a large trilinear coupling motivated by a first order phase transition, I cannot use the same strategy as I do for standard model. So in this plot, I show the significance of using the atlas-like cat. So in this cat, I require to be to gamma, and we can reconstruct a Higgs, and also vetoing extra jets and leptons to get rid of TT bar Higgs. So then for the new cat, I use exactly the same thing, but I remove the cat of MHH larger than 350, but I put a cat at MHH above 2m Higgs, but below 2m top. And then you can see there is a big improvement if I apply a new cat for values of lambda 3 that is much larger compared to the standard model. So I just show you how does a modified trilinear coupling can affect double Higgs. Now let's talk about this too. So an enhanced topic coupling and a new particle running in loop, and I'm going to use stops as an example. So with enhanced top coupling for double Higgs production, I still have these two diagrams, the triangle and box, but I have an enhanced top coupling here. And then I also have the same diagram but putting stops here instead of top. So they are diagram 3 and 8. And then for stops, I have the stop glue coupling. So I also have diagram 4 and 7. And for stops, I also have stop Higgs coupling. So they are diagram 5 and 6. And from those plots, you can see the contributions to double Higgs from stops depend on the mass of the stop and also the mixing of the stops. So when we talk about the stops for double Higgs production, there are some constraints that we need to consider. The first one is the modification in gluon fusion. So here I write down the effective Higgs-gluon coupling. This effective coupling increases as each top coupling increases. And that can be compensated by a mixing between the two stops. But then there is some constraint from the mixing. So if I have a too large trilinear term, I may have the problem of vacuum stability. So I use this estimation here. So basically it is saying the trilinear coupling squared should be smaller than the 3 m² squared. So this number may not be exact. Different calculations gives me a little bit different numbers, but the ballpark is it is smaller than 3 m² squared. And since there are stops, there are also constraints from direct stop searches. So here is the stop bounds from NCHEP. So from both Atlas and CMS, basically, if the neutralino mass is larger than 350, there's no bounce at all. So when I study the stop effect on double Higgs, I start from stop mass at 350. So I want to show you some very preliminary results. Here, MU and MQ are left-handed and right-handed stop mass. Each of them I start from 350. And in this plot, I didn't put any modification in the topic cover. And I only put stops in the loop. So in the dark orange region, the effective Huang-Higgs coupling is consistent with the current best fit value within 1 sigma. And then the light green region, this coupling is consistent with the current best value between 2 sigma. And then the green contours show the cross-section for Higgs, BB gamma gamma. The cross-section is in nanobar, and the standard model value is 60 nanobar. The blue contours shows the maximum xt that is allowed from vacuum stability. And so the largest value I got for this case is about 150. So it's about 150 nanobar. So that is a little bit more than twice the standard model value. So there's indeed some large difference here. And in this one, I modified kappa T to 1.2, so the top cover can be 20% larger compared to the standard model value. Again, in the green region, the gluon fusion is consistent with the current measurement within 1 sigma. In the red region, gluon fusion is consistent with the current measurement within 2 sigma. And then cross-section for BB gamma gamma channel, again, they are in nanobar. And standard model value is 60. So the largest value I got that also can be consistent with gluon fusion is about 300 nanobar. And that is about 6 times the standard model value. So that is a large effect. And here I didn't even put the modification in the trilinear coupling. So if I put the modification in trilinear coupling as well, then I would expect even larger modification to double Higgs. So in addition to double Higgs, I also want to mention boosted Higgs, because the things I just told you will also have an impact on boosted Higgs as well. So in the boosted region, which LHC has been pushing into, the triangle here cannot be treated as a point particle anymore. So that means when the BT of the Higgs is about the top mass, we should expect the full theory to be different with the EFT. And although we may not have sensitivity directly to the new particles in the loop, we may see the full theory to be different from EFT. And also, double Higgs is interesting because boosted Higgs is sensitive to the new particles in the loop. The reason is there are 2 diagrams here for boosted Higgs, the box and the triangle. They have different form factors. So then boosted Higgs will have some sensitivity to distinguish the loop particle. And also, if the loop particles are different and more decouples to Higgs differently with the tops, then we should expect the PT distribution to be different. So boosted Higgs will help us to break the degeneracy in gluon fusion as well. And also, boosted Higgs and the double Higgs is kind of complementary to each other, because for double Higgs, so double Higgs also has triangle diagram and box diagram. They are sensitive to the enhanced top coupling with different power, but for boosted Higgs, they are sensitive to the top coupling at the same power, but both of them have different form factors. So boosted Higgs, double Higgs, and TT bar Higgs together will help us to resolve the degeneracy in quantum fusion. So conclude here. So I show you an axis in TD bar Higgs channel. I don't even know if that axis is still there, but still I provide you two interpretations. The first one is the top coupling is standard model like the axis is actually from stop pair protection. And then in the second one, because I don't want it to be excluded so soon, I say we indeed have an enhanced TD bar Higgs coupling, but we have new physics to make the muon fusion standard model like. And this new physics will likely to show up in double Higgs and boosted Higgs. And also I show you double Higgs is also sensitive to the possible modification in the trilinear coupling, which can be modified for two reasons, because it is related to the nature of electroweak phase transition. So I'll stop here and take